Okay, I think we'll start now. So, have you gone through the problem statement? Anil Yogi, are you there?
Yes, sir, I'm here.
Yeah, so did you read the problem statement that was given in the tutorials channel?
Yes, sir, I've seen it now.
So, can you try to explain how you would go about trying to solve this?
Yes, sir, I'm thinking.
Sir, I have a question here.
Yeah,
So, because you have given that warp size is 16 threads, right?
correct.
So, are we still considering the global memory load with 128 bytes or 16 into 464 bytes?
16 into 4, 64 bytes.
Okay.
So there is also one more thing. So we are purposely asking you to ignore the effects of caching. So imagine you have a GPU architecture that doesn't have the L1 and L2 cache, and you just want to calculate the total number of global load transactions that are happening here.
Is it 1008 1008?
1008? Not exactly. It's lesser than that. Okay, maybe you can start explaining a bit. So how are you going about it?
So, there are 256 threads, right? 0 to 255, the
Correct.
IDs. And one warp has 16 threads, so there are 16 warps there.
Right.
And like you said, it is 16 into 464 bytes load
Right.
because we're considering float data type here. So,
Hmm.
uh, and each iteration that I is getting multiplied by 2. So in the
Correct.
first iteration, we are considering location 0 to 255.
Right.
So 0 to 255 means 256 threads are there, so there will be 16 loads.
Hmm.
And in
Correct.
the next iteration, we have I value equal to, so it is getting multiplied by 2, so we will have locations 0, 2, 4, 6, 8, and so on.
Right. So
So
you're basically getting a strided access there, right?
yes, so it will get multiplied by 2 the next time, the loads.
Correct. Correct. Okay. So that is a nice outline. That who is this, by the way? Naveen, right? So,
Yes, sir.
yes. Okay. So that's a very nice outline presented by Naveen. So maybe I'll try to explain this. So Anil, did you understand this explanation? Hello.
No, sir, not exactly.
Okay. So let's go about it a bit then. So note we are just talking about loads here. So we have an ATID times I. So there is essentially one store and one load happening in each iteration, but we are only going to focus on the loads here. So the way we would go about this is like we try to consider each iteration and try to calculate the total number of load transactions that are happening. Also, since the warp size is say 16, we assume that the axis width is essentially 16 times 4, that is 64 bytes. So let us try to see what is exactly happening. So say for I equal to 1, just a sec. Let me just share my screen. Is it visible? Hello?
Ah, yes, sir. Yes.
Okay, so let's say we have I equal to 1. So what elements of A are we now going to access? So let's say we consider warp 0. So I is 1 here, right? So essentially we are just going to be picking out a TID only. So essentially for warp 0, it will take just one global load transaction to fetch all the 16 elements into memory, right? Anil, are you understanding this part?
Yes, sir.
Okay, so naturally this would be the same case for the other warps as well. Say for 16 to 31, 32 to say 47, and so on. Now you have a total of 256 threads. Okay, so naturally if you have 256 threads, so you essentially have 256 threads, so you essentially have 16 warps. Okay, so naturally in one iteration, in the first iteration of this loop, you will essentially have, so since you have one global load transaction per warp, so you essentially have 16 load transactions happening in the first iteration. Is this part clear?
Yes, sir.
So can you tell me what would happen for I equal to 2? Hello?
In one qualist access, half of the threads will get their data. Like, so we need double the number of accesses.
Correct. So essentially you would now need 2 global load transactions per warp to fetch things, right? So essentially you're now accessing elements like this, essentially a stride of 2. So that essentially means you have 2 global load transactions per warp and thus a total of 32 load transactions. Now the next value of I is going to be 4. So you can naturally see the trend here. So for A now, it is going to be 0, 4, 8 like this, right? So this part now becomes four global and 64. Then say we have 8, 16, 32. So for now this essentially becomes 0, 8, 16, right? So can anybody tell me? So this would essentially become 8 global load transactions per warp, right? What about the last 2 iterations? Can anybody tell me?
256 and 256.
Correct. So for both the cases, so essentially here each warp would be able to fetch just one element, right? So there is no coalescing happening whatsoever. Is this part clear why that's happening? So say Aryendra Singh, are you there?
Yes, sir.
So can you tell me for the last 2 iterations, what like why did he
Yeah,
say the
yeah,
total of 256 load transactions?
yeah, we can like look at it like this, right? Ki if you are drawing 16 elements at a time, So, and using only one, or and in the 32 case, you are drawing 16 elements from one of the two rows. Like from 0th and first row, you are drawing 16 elements of 0, and then you are drawing 16 elements not from the first row but from the second row, right? So it's like 0th, second, and fourth, so on, and therefore the total number of loads is essentially the same.
Correct, because what's happening is the moment it actually kind of becomes the, what should I say, the value of I becomes the size of the warp or greater than that, essentially that means that like each warp would be able to fetch just one element for any of its load transactions. Is this part clear? Because your elements are now separated by a width that is greater than equal to your warp size. So anyways, for fetching 16 elements, one warp would now require 16 global load transactions. Hello, is this part okay?
Yes, sir. Yes, sir. Yes.
Okay, so I'm not completing this anymore. So this would essentially be 256. This would also be 256. And from here on, you can calculate the total. So what should it be? So 512. Here you have what, 1648 and 64. Is it somewhere around 752 or something like that?
Yes. Yes, it's
Okay. So someone mentioned he got like something over 1,000.
yes, sir. I didn't consider that this 256 for the last one.
Okay. Yeah. So now you understand why. Like it doesn't really matter if the value of I becomes greater than your warp size. Your number of load transactions become the same.
Correct. Correct. Yes. I
Okay.
got it.
Okay. So keep.
Axis width depends on warp size.
Correct.
32 multiplied by 4.
Right. So yes, but for this problem here, we've said that the warp size is 16.
Yes. Yes.
Okay, that's why we've considered the axis width to be 16 times 4 as well. Like it can also be the case that you might have a smaller warp size and a larger axis width. That can also be the case, but normally if it is not mentioned, then assume that whatever is your warp size, your axis width would be 4 times that number of bytes only. So keep this thing in mind, because like I think you have a short test coming up, I guess this next week. So like there will be certain questions based on calculating the number of memory access and all. So keep this thing in mind. So the key things that you should keep in mind would be like follow the warp size that is mentioned in the question, the axis width, whether we are asking you about load transactions, stored transactions, or both, or we are asking you about load transactions for a specific array or not, given a particular code snippet. So these are some of the examples that you can hope to get. Okay. So this was just one aspect of the tutorial that we wanted to cover today. The other one would be in explaining a shared memory problem. So I think you are now familiar with transpose and matrix multiplication and how shared memory is being used there, correct? So in the quotes that have been discussed in the slide, so you must have seen that whenever you are actually declaring shared memory, so you always declare it as a static, what should I say, as a static chunk of memory inside your kernel code, right? Hello?
Yes, Anirban, yeah.
So, in the previous question, the number of loads will be and stores will be same, right? Stores and loads.
Yeah.
Yeah. Okay.
Okay. So the total number of global transactions, if we include both loads and store, it will be times 2, whatever you got there. Okay. Hello.
Yes.
Yes, yes, yes.
Okay. So regarding the shared memory problem, so we'll talk about a code that is available on GitHub. So you'll see that NVIDIA basically has a blog series about certain optimizations and all the relevant code that they have discussed. So they've posted them on GitHub. So I'll share the link later on in the tutorials channel. First, let us go through this. So it's a very simple code. Essentially, you're just launching one block of CUDA threads only. And the job of that block is to essentially reverse a particular array with the help of shared memory. So they've implemented two functions for this. One is called static reverse, the other is called dynamic reverse. So say for static reverse, like you've seen in your past examples, you've declare a chunk of shared memory statically in the kernel code snippet like this, right? So, and what does reverse do? It just calculates the corresponding thread ID, calculates the index position of its reverse. It loads from the global memory D to shared memory T, does a sync threads, and then it again loads the shared memory at the position TR back into DT. So we again have that similar load, compute, load, that kind of mechanism that you normally have seen when people actually use shared memory optimizations. But this is probably the most simplistic case that you can hope to see. So does anybody have any doubts regarding this? What is happening here?
No, no.
This is like 1D transformation, right? Oh,
Yeah, it's a 1D transformation, and again, like it's an even more simpler case. Like you're just launching one CUDA block of threads. That's it. Like in the code snippet, you'll see that I'm just launching one block. If I launched multiple blocks, could I have like reversed it using shared memory, using this kernel only? Would that have been possible?
Calculation of TID would change.
Calculation of TID would change. Yes. So you'll have to load it using perhaps thread IDX for each block. But when you're going to actually pick up the elements from say DT and load them to DT, you have to rely on your global thread ID. So you can actually treat this as an exercise and try about doing this. Okay. But that is not the intention of today's tutorial. The intention is to teach you what this dynamic thing is. So this dynamic reverse, if you can see, the overall kernel code snippet is very similar to that of static reverse only, but there is just one subtle difference. I'm not explicitly mentioning the size of the memory here. Okay, I'm declaring it as an external variable, which actually signifies that this is being declared somewhere else. Okay, now the question is, where do I actually declare this? So this is actually done in the host code itself when I'm going to call that particular function. So if you have a look at static reverse and dynamic reverse, the only difference is this additional third argument that you can see here. Note, for this particular example, your block size was equal to the total number of elements of your array only because you were considering one block of CUDA threads processing the entire array, right? But beforehand, you do not really know what is the value of n, right? So for the static case, I had hard coded it to say 64. But if someone decided that he wants to reverse an array of size say 1024, then this code would not be able to run, right? You will get an access out of bounds error here the moment you try doing that. Whereas for dynamic reverse, the benefit of using that is you can specify the amount of shared memory that you want as the third argument in your kernel launch parameter call. This argument, so when the host program is going to run, it knows that, okay, this is the amount of bytes that has been reserved for the corresponding shared memory. And accordingly, it will parse that and populate this particular variable here subject to the size specified from the host program. Is this part okay?
So that
Yes.
variable S is not explicitly being declared outside somewhere. Where is it?
No, that is not explicitly going to be declared.
Okay.
So essentially the compiler itself will judge by inspecting the code that, okay, this is the amount of bytes you want to actually associate. And here it says that, okay, this is the shared
Sir,
memory that is there. Yes.
no, I couldn't hear you. I think you were inaudible.
Can you hear me now?
Yes.
Yeah.
So,
So as I,
so there can be only one external call in inside one kernel then.
correct. Not only one call, like you cannot really declare, say, a 2D shared memory tile that you were doing for, say, your matrix multiplication and transpose codes. You can only declare the total number of bytes to be reserved for that. Okay. So if you think about it in that light, how can one then go about implementing, say, a matrix multiplication using this? So you are restricted to creating only 1D shared memory tiles only. Okay, if you use the dynamic shared memory. Hello?
Yes, sir.
Yes, sir.
Okay, so can anybody tell me then what changes would I ideally need to do to my matrix multiplication code snippet to get that working?
So it will be like
Sure,
tile ij would become tile I times tile dimension plus j, something like that.
Correct, correct. Essentially, what would happen is like you're essentially declaring a shared memory of size tile dim star tile dim, and as far as accessing the shared memory becomes, you have to access them using our familiar row major notation of accessing that array. Okay, and I think corresponding to what Naveen asked last time, so is that part clear? You can only declare, say, one external variable only. The compiler's job is to inspect and allocate the required number of bytes there.
Yes.
Okay. Now, if keeping that in mind, so now you've also learned about this notion of padding as well, right? In the transpose thing, how to avoid shared bank conflicts and all. So
Yes.
as a takeaway assignment, I would suggest you try to figure out how dynamic shared memory, like if somebody uses dynamic shared memory instead of static shared memory for, say, implementing an optimized version of transpose that is free of shared bank conflicts, how can one person go about implementing that? So as one person suggested that for 2D tiled accesses, you would resort to your standard 1D type, like 1D method of accessing things. But how would that really change if padding is involved? So you try to think about this. We'll accordingly discuss this part again sometime next week, and we'll probably post a solution for that sometime soon.
So, sir, the only benefit of this is key you don't need to mention the size, and like it takes size according to what you're mentioning in terms.
What is actually demanded according to your inputs by your host program? That's it. So this has essentially ensures that given your problem, you try to work with the, what should I say, the minimal amount of shared memory that is actually required. In most cases, you try to, like, for problems where you are actually dealing with, what should I say, very large matrices, you would ideally want to use all of your shared memory that is possible to reduce your memory, sorry, to increase your memory bandwidth so as to make your application run faster. But in cases where, say, all that amount of shared memory is not really required, then it makes sense that you, depending upon your problem size, you allocate what is required for your given problem.
All right. Thank you, sir.
Okay. Okay, then. So we'll end it here. Does anybody have any particular doubts regarding these two aspects that we discussed? The coalescing thing, is that part completely clear? The total number of load transactions that we computed. If there is anybody who face difficulty in understanding this, ask me again. I'll explain that again here. Because that is going to be crucial for the upcoming exams that you are going to have, like be it your second short test or your long test. Okay then, so if there aren't any doubts, we'll then end it here. So I think like last time only, you will again have the exam on Monday for that same time only, 5:10 to 5:50. Regarding what is going to be like the pattern of questions, it is, I guess it's going to be similar as to what it was in the first short test only. And I think sir would later post an announcement later on Teams regarding the same.
Sir, what will be the syllabus?
Modules 3 and 4, I think it is mentioned there, right? So essentially your, I guess, warp scheduling, block scheduling, divergence, memory coalescing up till matrix multiplication.
Okay, sir.
Okay, and next week onwards, I think we should also start discussing about the term projects as well in a bit more detail. So I hope after this Monday's short test, all of you at least go through the papers once. Okay, we should start having some discussions in these tutorial classes from next week onwards. Also, I saw one person posting, say, the, like, I guess, creating a GitHub repository and adding the respective members there. So I would also suggest you add me there as well, so that I can also monitor your progress there. Okay, so my GitHub ID, I think, is there in the first tutorial post itself when I posted that particular repository HP3 lab. So when you're creating repositories, I'll also ask that you add me to them as well. Is that clear?
Yes, sir. Yes, I'll add.
Okay. Okay then. Okay, we'll end here. Best of luck for Monday. Bye.
Thank you, sir.